Fluid mechanics is a branch of physics concerned with the mechanics of fluids, liquids, gases, and plasmas, and the forces on them. Fluid mechanics has a wide range of applications, including mechanical engineering, civil engineering, chemical engineering, biomedical engineering, geophysics, astrophysics, and biology. Fluid mechanics can be divided into fluid statics, the study of fluids at rest, and fluid dynamics, the study of the effect of forces on fluid motion. It is a branch of continuum mechanics, a subject which models matter without using the information that it is made out of atoms, that is, it models matter from a macroscopic viewpoint rather than from microscopic. Fluid mechanics, especially fluid dynamics, is an active field of research with many problems that are partly or wholly unsolved. Fluid mechanics can be mathematically complex, and can best be solved by numerical methods, typically using computers. A modern discipline, called Computational Fluid Dynamics, CFD, is devoted to this approach to solving fluid mechanics problems. Particle image velocimetry, an experimental method for visualizing and analyzing fluid flow, also takes advantage of the highly visual nature of fluid flow. Brief history. The study of fluid mechanics goes back at least to the days of ancient Greece, when Archimedes investigated fluid statics and buoyancy and formulated his famous law known now as the Archimedes Principle, which was published in his work on floating bodies, generally considered to be the first major work on fluid mechanics. Rapid advancement in fluid mechanics began with Leonardo da Vinci, observations and experiments. Evangelista Torricelli invented the barometer, Isaac Newton investigated viscosity, and Blaise Pascal researched hydrostatics, formulated Pascal's law, and was continued by Daniel Bernoulli with the introduction of mathematical fluid dynamics in Hydrodynamica, 1739. Inviscid flow was further analyzed by various mathematicians, Leonhard Euler, Jean-Louis d'Alembert, Joseph Louis Lagrange, Pierre-Simon Laplace, Simeon Denis Poisson, and viscous flow was explored by a multitude of engineers including Jean-Leonard Marie Puiseux and Gotthilf Hagen. Further mathematical justification was provided by Claude Louis Navier and George Gabriel Stokes in the Navier-Stokes Equations, and boundary layers were investigated, Ludwig Prandtl, Theodore von Karman, while various scientists such as Osborne Reynolds, Andrei Kolmogorov, and Geoffrey Ingram Taylor advanced the understanding of fluid viscosity and turbulence. Main branches. Fluid statics. Fluid dynamics is a subdiscipline of fluid mechanics that deals with fluid flow, the science of liquids and gases in motion. Fluid dynamics offers a systematic structure which underlies these practical disciplines that embraces empirical and semi-empirical laws derived from flow measurement and used to solve practical problems. The solution to a fluid dynamics problem typically involves calculating various properties of the fluid, such as velocity, pressure, density, and temperature, as functions of space and time. It has several subdisciplines itself, including aerodynamics, the study of air and other gases in motion, and hydrodynamics, the study of liquids in motion. Fluid dynamics has a wide range of applications, including calculating forces and moments on aircraft, determining the mass flow rate of petroleum through pipelines, predicting evolving weather patterns, understanding nebulae in interstellar space, and modeling explosions. Some fluid dynamical principles are used in traffic engineering and crowd dynamics. Relationship to continuum mechanics. In a mechanical view, a fluid is a substance that does not support shear stress, that is why a fluid at rest has the shape of its containing vessel. A fluid at rest has no shear stress. Assumptions. The assumptions inherent to a fluid mechanical treatment of a physical system can be expressed in terms of mathematical equations. Fundamentally, every fluid mechanical system is assumed to obey conservation of mass, conservation of energy, conservation of momentum, The continuum assumption. For example, the assumption that mass is conserved means that for any fixed control volume, for example, a spherical volume, enclosed by a control surface, the rate of change of the mass contained in that volume is equal to the rate at which mass is passing through the surface from outside to inside, minus the rate at which mass is passing from inside to outside. This can be expressed as an equation in integral form over the control volume. The continuum assumption is an idealization of continuum mechanics under which fluids can be treated as continuous, even though, on a microscopic scale, they are composed of molecules. Under the continuum assumption, macroscopic, observed/measurable, properties such as density, pressure, temperature, and bulk velocity are taken to be well defined at infinitesimal volume elements, small in comparison to the characteristic length scale of the system, but large in comparison to molecular length scale. Fluid properties can vary continuously from one volume element to another and are average values of the molecular properties. The continuum hypothesis can lead to inaccurate results in applications like supersonic speed flows, or molecular flows on nanoscale. Those problems for which the continuum hypothesis fails, can be solved using statistical mechanics. To determine whether or not the continuum hypothesis applies, the Knudsen number, defined as the ratio of the molecular mean free path to the characteristic length scale, is evaluated. Problems with Knudsen numbers below 0.1 can be evaluated using the continuum hypothesis, but molecular approach, statistical mechanics, can be applied for all ranges of Knudsen numbers. Navier-Stokes equations. The Navier-Stokes equations, named after Claude Louis Navier and George Gabriel Stokes, are differential equations that describe the force balance at a given point within a fluid. Analogous to Newton's equations of motion, the Navier-Stokes equations describe changes in momentum, force, in response to pressure P\displaystyle Pp and viscosity, parameterized, here, by the kinematic viscosity nu\displaystyle\nu\nu. Occasionally, body forces, such as the gravitational force or Lorentz force, are added to the equations. Solutions of the Navier-Stokes equations for a given physical problem must be sought with the help of calculus. In practical terms, only the simplest case can be solved exactly in this way. These cases generally involve non-turbulent, steady flow in which the Reynolds number is small. For more complex cases, especially those involving turbulence, such as global weather systems, aerodynamics, hydrodynamics, and many more, solutions of the Navier-Stokes equations can currently only be found with the help of computers. This branch of science is called computational fluid dynamics. Inviscid and viscous fluids. An inviscid fluid has no viscosity, nu equals 0\displaystyle\nu equals 0\displaystyle\nu equals 0. In practice, an inviscid flow is an idealization, one that facilitates mathematical treatment. In fact, purely inviscid flows are only known to be realized in the case of superfluidity. Otherwise, fluids are generally viscous, a property that is often most important within a boundary layer near a solid surface, where the flow must match onto the no-slip condition at the solid. In some cases, the mathematics of a fluid mechanical system can be treated by assuming that the fluid outside of boundary layers is inviscid, and then matching its solution onto that for a thin laminar boundary layer. For fluid flow over a porous boundary, the fluid velocity can be discontinuous between the free fluid and the fluid in the porous media. This is related to the Beavers and Joseph condition. Further, it is useful at low subsonic speeds to assume that a gas is incompressible, that is, the density of the gas does not change even though the speed and static pressure change. Newtonian versus non-Newtonian fluids. A Newtonian fluid, named after Isaac Newton, is defined to be a fluid whose shear stress is linearly proportional to the velocity gradient in the direction perpendicular to the plane of shear. This definition means regardless of the forces acting on a fluid, it continues to flow. For example, water is a Newtonian fluid, because it continues to display fluid properties no matter how much it is stirred or mixed. A slightly less rigorous definition is that the drag of a small object being moved slowly through the fluid is proportional to the force applied to the object. Compare friction. Important fluids, like water as well as most gases, behave to good approximation as a Newtonian fluid under normal conditions on Earth. By contrast, stirring a non-Newtonian fluid can leave a hole behind. This will gradually fill up over time. This behavior is seen in materials such as pudding, oblak, or sand, although sand isn't strictly a fluid. Alternatively, stirring a non-Newtonian fluid can cause the viscosity to decrease, so the fluid appears thinner. This is seen in non-drip paints. There are many types of non-Newtonian fluids, as they are defined to be something that fails to obey a particular property. For example, most fluids with long molecular chains can react in a non-Newtonian manner. Equations for a Newtonian fluid. The constant of proportionality between the viscous stress tensor and the velocity gradient is known as the viscosity. For a Newtonian fluid, the viscosity, by definition, depends only on temperature and pressure, not on the forces acting upon it. In some applications, another rough broad division among fluids is made: ideal and non-ideal fluids. An ideal fluid is non-viscous and offers no resistance whatsoever to a shearing force. An ideal fluid really does not exist, but in some calculations, the assumption is justifiable. One example of this is the flow far from solid surfaces. In many cases, the viscous effects are concentrated near the solid boundaries, such as in boundary layers, while in regions of the flow field far away from the boundaries the viscous effects can be neglected and the fluid there is treated as it were inviscid, ideal flow. When the viscosity is neglected, the term containing the viscous stress tensor tau \math\tau\math\tau in the Navier-Stokes equation vanishes. The equation reduced in this form is called the Euler equation.
Please subscribe and thanks for watching.